lights in here.
Sure. Too much.
I know.
There you go.
How's that?
I can read with that. Beam me up. Well, good evening, everyone, and welcome to the RASC Winnipeg Center's annual or monthly meeting. And for those online, welcome. I see we've got Jim McGregor, Stephen Hudley, Darren Gillis, Michelle, Danielle, and a few others out there. So all of you is welcome, and those that are joining us on Facebook Live as well. So we start off our meeting. I'll just do a land acknowledgement. The lands from which our members and guests are joining us are located on the original lands of Anishinaabe, Cree, OJ Cree, Dakota, and Dene peoples, and on the homeland of the Métis Nation. We respect the treaties that were made on these territories. We acknowledge the harms and mistakes of the past, and we dedicate ourselves to move forward in partnership with Indigenous communities in a spirit of reconciliation and collaboration. So I would now ask, and please get you to welcome our beginner session host tonight, Mr. Scott Young. Please welcome Scott Young.
Thanks, Dennis. Okay. I was asked to do some beginners session stuff today, and I told Judy I would talk about meteors and constellations and the Milky Way and stuff like that, intending to send her a real talk title later, and I never did. So today's talk is entitled Meteors and Constellations and the Milky Way and stuff like that. Let me get to our presentation here. And yeah, sure. The mouse is not happy. No, the mouse is actually not functioning. Oh, wait, it might be functioning. No, it is not functioning. Can we see the pointer anywhere? Oh,
What's function?
oh, okay, yeah, but that's there. Okay, okay. So first we'll do slideshow, and then we'll go back to Zoom and share screen. I think that's how this works. Okay, so hopefully that's also showing up in Zoom land. Okay. And we'll get rid of some of that. All right. So summer is the time to look at meteors. At least that's what the media has been telling us for 2 weeks. There was a double meteor shower that occurred on July 31st that I was entertained to learn about when a reporter called me and asked me to talk about it. There were 2 meteor showers peaking on that day. One of them produces 7 meteors per hour, and one of them produces 1 meteor per hour if you're in the southern hemisphere. But they both showed up in a calendar, and so they became a story. Well, space sells. If you want to generate clicks, talk about space stuff. So this is the problem with meteors. How many people have seen a meteor shower that has blown you away? Okay. How many of you are referring to the 2001 Leonid meteor shower? Yeah. That was the one where we drove into North Dakota because it was cloudy here. And I think we saw, I don't know, I think our group's count was 3,000 meteors in a few hours. That was amazing. Almost every other meteor shower, it's not really a shower. It's a meteor spritz. People get excited and they think that they're going to see all these meteors. If the best thing about a meteor shower is it's a date on the calendar that gives you an excuse to drive out of the city and stay up all night looking at the stars. If you see meteors, great. But if you don't, a night under the stars is always well spent. So we're going to talk a little bit about meteors, but also the other things you can see in between meteors, which is largely what you'll be spending your time looking at. There we go. Summer is Milky Way season. So if you're out under a dark sky, you're going to drive away from city lights to see the meteor shower, you're going to get a great view of the Milky Way. especially as we come up to the Perseid meteor shower, which is coming up on the 11th and 12th. We have a first quarter moon then. That means the moon will set around midnight, and it will be nice and dark skies after that for the prime of the meteor shower observing. So that is the time you really want to get out and look at the meteor shower. It's also a great time to see the Milky Way and all of the constellations that are sort of scattered along there. We have a beautiful view all the way down. Do we have a pointer here? Show up here? Yeah. Down from Sagittarius, down in the southern horizon, the center of the Milky Way, stretching all the way up through the summer triangle, through Cygnus up here with the dark lanes, and stretching all the way across the sky. It pretty much goes almost straight overhead when you're getting out into the night. And if you can get away from the city lights, it really is a beautiful sight. Now, normally I would suggest take your binoculars out or a small telescope and just scan around in there. There's piles of things to look at. Don't do that on the meteor shower night though, because you won't see any of the meteors. You want to just keep your eyes open and not use any optical aid to see meteors. Anytime you look through something, you're cutting your view down, sometimes to a small circle, sometimes to a really small circle. And the odds of a meteor going through your field of view go way, way down. So if you want to see meteors, you really want to keep your eyes wide open at 1x magnification. And so you can spend that time appreciating the beauty of our galaxy from the inside just with your eyes. That's a good night all on its own. You go out and spend 3 hours under the Milky Way and you look at the constellations and you feel the motion of the planet as it rises and sets, and you come to terms with your place in the universe and you contemplate all the big questions and things like that. Ideally, you've got some friends out there with you and you're chatting about all sorts of things. That's a good night without any meteors. And that might be what you're going to have happen, because I've gone out for many Perseid meteor showers and I made a lot of mistakes, which I'll share with you, but it's real easy to miss a meteor. A meteor is a tiny piece of dust from outer space, and it crashes into the Earth at speeds of 10,000 kilometers an hour, something like that. And it just vaporizes in a flash of light that lasts for a second. Don't blink or you'll miss it. Don't look down at your phone or you'll miss it. Not just because you're looking down, but because you've looked at a light that has now destroyed your night vision for 5 minutes and you won't see any meteors at all. So to see meteors, you really need to eliminate all the lights, unplug from the electronic devices, and just let your eyes soak in the light from the universe. You can't even look away. I don't know how many times I've been out at Glenlee for a Perseid or whatever meteor shower, and I'll turn over to somebody to say something, and I'll see my shadow cast on the ground, and everybody will go, "Oh, look over there." And by the time I've turned my head, I've missed it. So you really need to spend time looking at the sky if you want to see those high rates of meteors. This is what people expect. This is the Leonid shower of 1833. The stars fell like rain, as seen in this original photograph from 1833. This is a woodcut, I think, trying to give the impression. They figure 150,000 meteors per hour at the peak rate. And that's, obviously an estimate. That's amazing. That is not going to happen when you go out looking for meteors. If it does happen, it'll be cloudy that night. That seems to be the case. But on the other hand, the other way to look at it, the optimist way to look at it, this could happen any meteor shower. We could go through a big clump of material that nobody even knows was there, and suddenly you could get a burst of activity. That happened just a little while ago. This is the live camera from the Subaru telescope in Hawaii. And there's this webpage I follow, a YouTube channel that I follow, Asahai Astro. And he basically just rebroadcast their live view. And all of a sudden, there were like 15 meteors that all came in, all parallel in the same angle and things like that. Really, really cool. Okay, well, now the mouse worked. See if we'll be able to. Oh, it's going to show me an ad, really? Had this all set up so it won't. Okay, well, we won't worry about that. There's the video of this is captured on the Asahi Astro Live's YouTube channel, so you can just take a look at it. And it's in real time. It just shows what it would be like if you were there to see it. That could happen anytime. So if you're an optimist, the more time you spend out there under the stars with your eyes open, the more chance you have to see something spectacular like that. Probably you'll see individual meteors one at a time, and probably you'll miss some of them. And that's just the way it kind of goes. So why are we looking at meteors anyway? These little pieces of dust, the size of a grain of sand, are leftovers from the formation of the solar system. The formation of the planet is still happening now. The accretion or the collection of materials is still happening as we speak. And every day the Earth gets hit by about 10,000 tons of interstellar dust as we go in our orbit around the sun. And that amount of material burns up in our atmosphere. So every one of those that we're seeing comes from the early days from before our planet was even born. Now, during a meteor shower, we go through a little bit of a different situation. You know, in your house, you've got dust, a little bit of dust everywhere, but there's certain spots, especially if you have a cat, where the dust collects. And so you get these dust bunnies or dust rhinos or dust elephants or whatever. Same thing in space. Space has places where there's more and more dust. And so if the Earth goes through one of these cosmic dust bunnies, we get a lot of meteors that night. Cosmic dust bunnies are left behind by comets as they go around the sun. These little ice balls that come near the sun, they melt, they spew off a tail of material that looks beautiful. They're gone a few weeks later, and then maybe we never see them again. But that material is left in its orbital path. So basically, it's leaving dust bunnies behind it. And if that trail happens to intersect the Earth's orbit, that means that every year at the same time as we go around the sun, we'll go through the, I thought I had a soundtrack here for a minute. We'll go through the trail of that comet, and we will see a bunch of meteors. We are going to use a little loop here. This is the situation. This is a great site called meteorshowers.org, and you can go to it and look at a 3D model of the trail of the comet that is leaving the Perseid dust bunnies. And so here's the material. The white line is the comet's orbit, and the blue line right in the middle there's the Earth just moving around. And every 11th and 12th of August, we go zooming through that trail. Now, if you look at it from a different angle, it's kind of plunging down on us from up above. So the Perseids are a northern hemisphere event. If you live in the southern hemisphere, the Perseids are not a big deal at all, because most of the meteors have already burned up before they get down to where you are. Here in the north, it's pretty good. But if you go too far north, in August, it's not dark. And so there's really a zone of sort of 20 to 50 degrees that is the perfect zone for watching the Perseids. That's the latitude there. This is a fun little app. You can set yourself up to be on the Earth. And here we are on the Earth flying through. And if you turn on everything at once, you can sort of see what a crowded pile of dust bunnies there are here. There's the Earth zooming around through the middle of all of these little orbital trails left behind by different comets. Okay, anyway, we'll come back to here. Which one is the show? So, if you want to see meteor showers, or you want to see meteors, the best time to go out is during a meteor shower. We've got one coming up. It's already started. We started going through the outer edge of the dust bunny right now. So you might see meteors at any point, but there are two factors that will affect how much you see. One is how close you are to the night of the peak. The peak this year happens to be August 11th and 12th. So that's the time that you want to go. The night before, probably still not bad, maybe half as many meteors. The night after, probably half as many meteors. It sort of goes up over a couple of days and then fades down over a couple of days. The other thing, though, is where you're located on the Earth. And we'll get to that in a second here. I have my slides in the wrong order from what I thought they were. How many of you have actually been on a train? A few people. Okay, great. I love the train. It's a great way to travel. The tracks do not actually converge like this. They're parallel because obviously the train doesn't get skinnier as it goes through space. The tracks are parallel, but our perspective here makes it look like they go off into infinity and meet in the center here. Any two parallel lines would do that. Meteors are coming in from outer space at us in pretty much parallel lines. That orbit is pretty much at a certain angle, and all the particles are following that angle. But when they come at us, because of our perspective, just like the railroad tracks, they appear to diverge from a certain point in the sky. That point is called the radiant, and that radiant is in a certain part of the sky. For the Perseids, that radiant is in the constellation Perseus, and that's why we call it the Perseids. The Capricornids have their radiant in the constellation of Capricorn, and so on. That doesn't matter for us observing the sky very much. It mostly matters for people that are studying meteor showers and trying to classify them to figure out which object they came from and that kind of stuff. There are over 100 meteor showers that have been cataloged. There's only 2 or maybe 3 that I even bother getting up for because most of them are 1 meteor per hour or less. So the Perseids is one of those 3. And so its radiant is in the constellation Perseus. And the constellation Perseus is down below Cassiopeia in the northeast after midnight. So the meteors are going to be coming generally from the northeast. And that doesn't mean you want to look northeast because the meteors could appear over here or above you or down below the ground. That's just the direction that they're all going to come from. If you want to take a picture and have meteors all radiating from one point, that's maybe a place to look at. But when you go outside, the best place to look is pretty much straight up because you want to get to see the darkest part of the sky where you can see the faintest things, and that will let you see the most number of meteors. This is I hate doing graphs, but it's kind of important for this. This is observations of last year's Perseids by radio. It's hard to see meteors in the daytime because they're not bright enough, but radio observers don't care about that. They can actually track meteors 24/7. And so using the radio system, they were able to tell that basically the peak was at a specific time here, and then it sort of faded down, and then it peaked again about almost a day and a half later. So that's the kind of behavior that the Perseids have. They have this sort of first initial peak, and then it sort of goes down a bit, peaks again, and then comes down. So that's the kind of activity that we expect to see. That gives us several days to see the Perseids. This is the slide that I thought was coming up before. This is the most important factor on whether you will see lots of meteors or not. When you go out. For years as a kid, I joined the RASC when I was 17, I think, and I would go out for the Perseids every night. We'd get that observer's handbook and I'd figure out the universal time when it was going to peak. And I would go outside that night and I would see nothing, like literally nothing, and for hours. And I might see 1 or 2 because I had a bedtime of 11 o'clock. Well, that did not work very well. Most meteor showers, effectively all meteor showers, are best between about 3 and 5 in the morning. That's just the way it is. It doesn't matter when the peak is. It doesn't matter when we're in the middle of the dust bunny. This factor overwhelms everything else. And it's because of the way the Earth is moving around the sun. In this diagram, the Earth is moving sort of counterclockwise, and it's also spinning counterclockwise. The meteors before midnight are basically coming in from behind us, and they have to be going fast enough to catch up to us and go through the atmosphere and burn up. The ones when we're after midnight, we're basically on the front of the Earth as it plows into the meteors, and that's when everything that we hit becomes visible. So if you want to see meteors and you're not willing to get up at 3 a.m, you're not going to see meteors. I mean, you'll see a few. There are some in the evening, a few. And if you make all your other things perfect, like you get away from the city and you can avoid the moon and all those kinds of things, you'll see a few in the evening. But all of the peak numbers that you see quoted in the media are all that morning kind of thing. How many will we see for the Perseids? I'm guessing 42 per hour. And that is not really fully scientific, but it's based on the conditions that we have and the height of the radiant for us here in Winnipeg and the time that we'll be going through. That's still pretty good. That's a meteor every 90 seconds or so. If you're able to watch the sky and not look away, 40 meteors per hour is pretty good. If you have a camera, you'll catch even more because it'll catch some of the fainter ones maybe. So that's definitely worth getting up for. Off on, here we are, this is the sky about 3 a.m, on the morning of the Perseid peak. And in the upper left there, you can see the Perseid peak. That's where the radiant is. Down below it is Mars and Jupiter, nice side by side. I will have to fight my inclination to set up my telescope and look at those instead of trying to concentrate on seeing meteors. But we have a pretty nice view of a bunch of constellations. Now look at all those meteors on the other side, or meteor showers on the other side of the sky. We have the Northern Iota Aquariids and the Alpha Capricornids, the Southern Iota Aquariids, the Southern Delta Aquariids, the Alpha Pisces Australids. All of those combined on the night of the Perseids will produce 2 meteors per hour. So you might occasionally see a meteor that isn't coming from Perseus, but it could just as easily be some of that random dust that will also be happening. There's these 3 different sources of meteors. There's the Perseids, there's the general background sporadic layer of a few meteors per hour, and then there's all these other little showers over here producing a few meteors. So it is a good time to go out and observe. And on the meteor shower calendar, there's lots of peaks in summertime. So that's why we hear so much about meteors at this time of the year. And that's why the Perseids are probably the most famous, if not the best, meteor shower ever. Let's see here. This is looking the other way, off towards the north. So Perseus is actually over on the right side of the screen there. You can see Mars and Jupiter as well. There are a couple of other meteors, the Kappa Cygnids. I don't know that I've ever seen any of those. They're also a very low number. But we have the northern sky, perhaps some aurora with all the solar activity. I wouldn't be too surprised. And the stars of the summer triangle, the Milky Way arching across the whole sky. Even if you don't see any meteors, this is a beautiful vista to look at and gives us a nice sense of all the things that are up there in the evening sky. I wanted to show this last site here. This is a place called livemeteors.com. And it basically, remember I said you could detect meteors through radio? This basically just has a radio telescope looking at the sky. And every time a meteor comes in, it ionizes a layer of air and suddenly radio waves bounce off it for a second or so, and it gets detected. So coming up on the Perseids, sometimes I'll put this on and just see how many meteors come in during the daytime, because we won't be able to see them visually, but you can actually detect them this way. And so that's livemeteors.com, and they usually do live stuff through YouTube during the event, during the main part of the Perseids as well. Now let's go back to our okay. If the Perseids are not the best meteor shower, what is? Anyone have an opinion? Oh, okay. Yeah, the Geminids are, I think, the most reliable meteor shower. They actually do well before midnight. That's the only meteor shower that does that. They're generally bright. They happen December 13th and 14th, so they're less popular with people that like to keep their limbs unfrozen. But there's no mosquitoes. I have never been bitten by a mosquito during a Geminid meteor shower. The Perseids, I lose a pint of blood every single time. There's another meteor shower in January called the Quadrantids. Most people don't go out to see it because it has a very narrow peak. It goes up from nothing to its peak of 100 meteors per hour and down again in 16 hours. So that can happen almost without us being able to see it at all based on, where it's daytime and where it's nighttime. So that's a challenging one to see, but it produces a lot of meteors if the time works out. And then, of course, as we said earlier, there are the Leonid meteors. The Leonid meteors are left by a comet that leaves material behind. Every 33 years, it goes around the sun. And every 33 years, it comes and makes a fresh trail of material. That's what we used to think, at least. And the Earth would go through that, and we get these meteor storms, the 1833, 1866. There was one in 1900. There was one in 1933, 1966. We all went out in 1999, and it didn't happen. Happened 2 years later. Turns out that it's not quite as simple as going out the same year that the comet goes through. And now we have to model the particle orbits that come out as the comet's orbit changes over time. And it gets very, very complicated to figure out when these storms are going to happen. But we're getting better at them. We knew that 2001 was going to be a great time, enough that we drove to North Dakota for it. So that was great. If you want to see lots of meteors, that's what you got to do. You either have to be ready to go to one of these storm events, which are very, very rare, or you just got to spend a lot of time under the stars and see what happens, because the meteors don't come in on a schedule. They don't care how many hours you drove or how much you want to see them or whatever. They happen on their own schedule, like everything else in the universe. And so it's kind of amazing that we can even predict at this level, this particular night is a good night to go out and see them. So I hope you have some success observing the Perseids. I know there's going to be some people out at Glen Lee the night of the 11th into the 12th, and I know that there's some people heading to Birds Hill as well. The planetarium is going to live stream again. Hopefully we'll be able to see some that way as well. So join us for the Perseids, and even if we don't see any meteors, it's going to be a good night under the stars. Any questions? Oh, Judy.
I just like to say that when you do look at Perseids to see the meteors, you notice that some are coming so much toward you that they just are a little flash, and you can miss them really easily. But
Right.
if you counted those, there would probably be more than you would see going past your eye.
Right.
Up in the sky.
Right, that's a good point. So when you look at Perseus, just to repeat for the folks online, there are meteors that are coming almost straight to you. And so they're very short trails. Whereas if you look off to the side, they're kind of going out like this and they're very easy to see. So maybe there's a lot of them there that either happen so quickly you miss them, or you just think, did I really see that or not? I don't know how many times I think I see something at the limit of my vision and then I don't count it, because I think, no, I'm just imagining it. But maybe those are the ones that we see. Yeah. Any other questions? This is a daytime meteor. Anybody ever seen one of those? Really? Oh, wow. You've seen everything. That's awesome. Wow. I've never seen a daytime meteor, but I've got lots of phone calls about them. And we've gone out in the field a few times to try and triangulate and things like that. Very, very rare, but something that, again, could happen anytime. So keep your eyes in the skies. Okay, thanks. Where is the... Thank you.
Thank you very much, Scott. go. Thank you very much. Again, thank you very much to Scott for doing our beginner session tonight. And the lineup for tonight, meeting welcome by myself, Dennis Lyons. I am the president of the RASC Winnipeg Center. We'll talk a little bit about announcements. Brian Stack will do our What's Up tonight. Florent Thibault will do What's New. Then we'll have our break, and then our main presentation by Dr. Tyrone Woods. Castor getting ready for Canada's first flagship space telescope. And as usual, after the meeting, all are welcome over at Boston Pizza on Pembina. So just a reminder of a few things. Lockhart Planetarium at the University of Manitoba. It's on their website. If you go there to find out when they have their public events, and Dr. Danielle Pahud is the person who coordinates that. Our observatory committee, if you have anything you want to know about the observatory, you can contact Michelle Boyce. For in the audience, Michelle, do you want to hold your hand up? Michelle's over here. And Explore the Universe, we have Stan Runge. Stan, I know you're here. Where are you? There's Stan right there. So if you have any interest or want to learn about Explore the Universe, please talk to Stan. It's an observing program to help everyone get out there and get started, and gives you a bit of an idea what to look at. Because sometimes, like Scott said, you go out there and you see, and they've got this great big beautiful sky. What do I want to look at? And that program kind of gives you a bit of a guide and gets you started into things. And you can either do it visual, meaning just with your eyes, or also with binoculars. You can use scopes too. But it's a very easy program to get you going and orient yourself to the sky. Our fundraising committee is Wing Kwong. Wing, I saw you here earlier. Wing's over here. Again, if you got any questions about that. Our telescope loaner program, Mike Caracas. Mike is here tonight. So Mike Caracas is over here. Mike, did you want to say anything about the loaner scope?
Very successful. As far as
So for those who are online, Mike just mentioned that next week, the scopes will be coming back. So they're available to take out, and it's a membership privilege. It's one of the benefits of being a member of the RASC Winnipeg Center. We have scopes for you to borrow, for all different levels of experience, including a solar scope, as well as some equipment to set you up if you have your camera for astrophotography and things like that. And if you're saying, geez, I wonder if I should go out to Spruce Woods for the star party, but I don't have a scope, I won't know what to do. That would be a good time to get a hold of Mike and reserve one of the scopes. And then I'm kind of leading in here without doing it. And then over to Damon, if Damon wants to talk a little bit about the Spruce Woods Star Party.
So Spruce Woods Star Party starts August 30th, goes till Labor Day Monday. Stan over here is taking registration still. Should be really good this year. We also will be at Spruce Woods next weekend for our annual public event with them, and we'll be at Criddle Lane Homestead, the Natural Heritage Site the next night, doing a public event there. So thank you for everybody that's volunteering for all that stuff.
So again, for those online who may not have heard that, for the public event at Spruce Woods Star Party is next weekend, and at the Criddle Lane Heritage facility as well the second night. And then of course August 30th for the long weekend is the Spruce Woods Star Party. If for those who are interested, Stan Runge is taking membership or registration. And as well online, if you're online, you can register if you go to again, you need to be a member of the RASC Winnipeg Center or a member of the RASC. And if you go to our website, there is information to be able to register there online. And you can pay by an e-transfer as well, or check or cash to Stan, depending on the arrangements you make with him.
We could take registrations on site day of the event, but we would prefer to know that's.
And again, it was just mentioned that you can register right up to and including the day when we start out at Spruce Woods. It just makes it easier for planning for the team to know how many people are going to be there. Because on the last day, there is a hot breakfast that's being prepared. So we just need to plan for those sorts of things. So if you're coming, let us know. We'd love to see you out there. It's usually an awesome time. And regardless of what the sky events are, we all have a good time chatting up and enjoying the weather. So I put my glasses back on. If you have any workshop ideas or would like to volunteer for workshops, again, Stan Runge is our workshop coordinator. We'll be looking at starting that up again in the fall with some new ones. But if you have any ideas or things you'd like to do, please let them know. And again, those are meant for, generally speaking, for the membership of the RASC. If you're not picking up on it, I'm trying to make a pitch. If you're not already a member of the RASC, perhaps you might want to look at us. For September, there's an outreach at U of M. If you're interested, please let us know to volunteer. Also now, it may seem early, but it always creeps up on us super fast. Nominating committee, our AGM is usually early in the new year. It used to be January. We might push it out just because of financials. We may not have enough time to do financials, but of course we have elections. And our nominating committee this year is myself and and Stan Runge. No, sorry, Scott Young. I said Stan, Scott. I had a brain fart there. Stan is busy doing lots of other volunteer work. The positions that are open is the president, the vice president, treasurer, and counselor positions. So if any of those are interested and you want more information, please contact us. We'd love to talk to you about it. And I cannot encourage you enough to, please, if you think about it, please take an opportunity to come and serve the council to help all the different things that happen for us. They meet once a month and maybe one or two other, or there might be some other, an hour or two looking at things or responding to emails in between the meetings. So it's not a huge commitment, but it really makes a huge difference for the things we're able to do for the center. Glen Lee, repairs are being worked on over the summer. Members in their observing night in the future, there is one tomorrow, it's scheduled, and Wing, I believe, is you're hosting tomorrow night, and he's got a bunch of different types of scopes that he's going to be demonstrating. Is that correct, Wing?
Smart scopes. Yeah.
So if you want to know, there's lots of talk about new smart scopes out there. If you want to see what they're like, come on out. Again, that's a benefit of being a member of the RASC Winnipeg Center. The other thing I wanted to pass on is what we've decided is rather than for years we've had members observing night is the night following this open meeting. We're going to be adjusting some of the nights to match up better with some of the celestial events that are going on. So it makes more sense because sometimes it's a full moon, and unless you're working on the moon, looking at the moon, it's not really a good night for going out and learning things. It's still a great night to come on out, see the observatory, learn a little bit about what the facility has. It's always a good night for conversation and chatting, or if you come out and somebody's there that might be able to help you with a problem you might be having, it's always good to come out. But one of the reasons we're adjusting the schedule a little bit is so that we have more things to look at when we go out. Dark Sky Preserve, just so people know, we've been working, the RASC Winnipeg Center worked first with the Spruce Woods Provincial Park, and they've got their designation as a Dark Sky Preserve. We're still working with the Nature Conservancy of Canada for the Weston Family Farmhouse Dark Sky, but the Tall Grass Prairie is really what it is, Dark Sky Preserve. And there is a documentary work that's going to be filming. So you may see them out at Spruce Woods at a couple of the events filming. It is something we've talked to the producer and director, and just want to make people aware that that's going on. They're just trying to get some pieces of information from all of it to put together and kind of showcase that it's a lot of work and a lot of volunteer hours to be able to go from, hey, we really want like this. We want to preserve this area for a dark sky for multiple reasons, and just to capture what it is to do that. So you may see that if you go out to any of the events, just be aware of it. That's all. And calendars have been bought for those that were looking for them. They're not published yet, but when they do come out, it's a limited quantity that we'll have here for the center. So when we do make the announcement, you need to move quickly because we're not bringing in as many as we have in the past, and we're just going to see what the response is to buy them locally. So that's a bit of an advance notice for the calendars. Yes.
Did you take pre-order commitments?
Yes.
Who said yes? Stan, there you go. Okay, Stan says yes. Stan loves, so Stan says yes, then we're going to. So you'd contact Stan and we'll go from there. Any other questions? No other questions. Oh, wait. Oh, Judy's got her hand up.
I just got an email, I don't know if anybody, I know one of the persons submitted pictures to the calendar contest. I just got an email that said, pictures Jay and I did. It's in the calendar this year, and it's the Perseid meteor show.
Oh, congratulations. Now, is that appropriate? You know, Scott's a little prescient there, you know, hey, look at that. Let's talk Perseid. Go ahead, Stan.
Calendars. Because I was talking with Mark, but the two of us would sell off the calendar. And because there's a limited number, so we're gonna ask members only to be able to buy one at a time, or to buy one. So that'll give the most number of members. So when there's talks about pre-ordering, he's gonna put his name down for one already. And after the majority of members have had their chance to get to one, then whatever's left will allow to get bottoms to second and third. So if you're serious about getting a calendar, get them now, and the price of it will be significantly less than ordering it through national. Because national charges you a big a higher cost per calendar plus higher postage cost.
Shipping and handling. Shipping and handling is, postage has gone way out. Anybody got anything they'd like to share or ask? Oh, I have to do it to you. Do you know why the pepper could not take part in archery? He didn't have an arrow.
Already assaulted.
Oh, it's getting good. So this slide here, just simply our meeting schedule for the fall into Christmas. There are some slight changes. This will be posted on the website as well. Just to let people know the idea. And then in particular, the December 6th meeting, because this room will be in use. The Schultz Theater is just down the hall, and we'll be set up, and you'll see it. We'll be set up on that date, and you'll notice it. It's just a smaller venue than this. So that's just to let people know, give you a heads up that some of the dates are slightly different for various reasons. Again, just a reminder, groups.io is our primary means of communication with the membership. And on there is different groups you can join. So there's, if you're trying to sell something, that's a good place. There's an area there, subgroup you can sell things on. And surprisingly, it's been fairly active the last little while. And several other information and subgroups if you're interested. So sketching, things like that. Not a sketchy site, sketching. Members of observing night, Wayne, are you doing 8 o'clock? What time do you are you going to be out there?
I'll be there by 8.
So 8 o'clock, it'll be open at that point. And I'd like to introduce our next speaker now for What's Up, Brian Stack. Please welcome Brian Stack.
Oh, you're too kind.
There you go.
That's when we need the dad joke.
Say something.
Yep.
It's my first one. It's too neat. All right. How do I look? Yeah. Use that pointer.
It's right there.
Here you go.
Okay, so we're going to talk about for the what's up for the night sky for August.
Right.
Not on?
There
Okay. Is that better?
Yeah.
Sweet Jesus. How about this? Okay.
that better? Okay, so we'll talk about the events that's happening for August 2024. This is it's in the way. It is in the way. Okay. We'll talk a little bit about the planets. Okay, so basically Mercury is going to be it's going to fade out in the last half of the month. Venus is going to be very low in the evening twilight. Now for Mars, Jupiter, and can I move this? Okay, we're just going to leave it. Okay. For Mars, Jupiter, and Saturn. Okay, it disappeared. Great. So Mars and Jupiter are going to rise after 1 a.m., where Saturn's going to start to rise after 10 p.m. Tomorrow evening, but then thereafter it's going to rise a little sooner and sooner. So by the star party, it should rise around 9:30. Okay, now there's a lot of events that's happening here, but there's only two that I'm going to really point out. We do have alignment of planets on August the 28th, but you'll see that Mars is only 5 degrees south of the moon. But you're going to take two events from this list, and I'm going to point it out. Basically, the meteor shower on the 12th, the Perseid meteor shower, and of course, the star party on August the 30th. Please take away from two events if you can read that. Okay, now for tomorrow's night at the members, we do have, in terms of it, there's not much of a Milky Way happening here. For this year, it's not great. We do have some of the major constellations, Hercules with M92, the Pegasus, with Andromeda Galaxy of M31, and we also have the summer triangular that's still happening and still quite high in the early evening. There's one thing I am going to point out. Saturn, this doesn't represent a good, Saturn is much higher than it really is in this picture. So I pointed it out right there. But one thing I kind of failed to mention earlier is the tilt of the rings. It's only going to be about 8 degrees. So what I've done is kind of blow it up for you. So that's what's happening with Saturn. It's going to get worse. The rings are going to disappear eventually, and then a bit better over the years. So it's going to be a gradual one. Now, as I mentioned here, this is the summer triangular that we have. Is composed of 3 stars, Deneb, Vega, and Altair. So as I here, so it's hard Deneb to Vega to Altair, and then back to Deneb. So that's the summer triangular, and it's still going to be quite visible high in the sky for the month. Now, Scott kind of mentioned about this. This meteor shower is still active, and why I want to mention it because it's, even though it peaked on July the 29th, it's still active. So what this means after the Perseid meteor shower that's happening on the 12th, so there's a greater chance of seeing something happening in the next few days. Scott did point out, yes, it's in the pre-dawn of August the 12th, but it's rated to be 110 per hour, but it's only been observed as 40, as you mentioned. But the moon's going to set in plenty of time for us to observe it. Again, like you mentioned it, most of us are probably going to be at Glen Lee on Sunday. And the weather looks really good. Okay, so here I have August the 28th. I'm going to talk a little bit more closer to the star party now because there's a lot happening for the star party. And I don't want to miss anything out. As I mentioned, this is the alignment of planets. We have, of course, Mars, Jupiter, Uranus, and Neptune and Saturn. So those planets are going to line up, but it's not going to happen until after 1 a.m. in the morning. And it's going to be pretty much dominant for the rest of the month. Again, I have here again Saturn. The rings tilt is only going to be roughly 8 degrees. Now, as I mentioned earlier, again, there's not going to be much of the Milky Way. I had a look on August the 30th to see what's going to be like. But as you can see here, we really don't have much of the Milky Way. It's going to be a very small amount of it. But we do have the major constellation. We have Pegasus, the summer triangular. We have Hercules with M92 and M13 star cluster. And of course, the double star cluster here. It's really nice to observe when you have dark skies. Okay, for this one here, now this is for Saturday morning in the pre-dawn. This is about 4:45 on Saturday. Of course, we have Orion that's going to come up, a winter constellation. But one of the things I want to point out here is we do have the thin crescent moon pointed right about there. And we'll just blow it up a little bit for you because you can't see it. So we do have a thin crescent moon on Saturday morning, and we're probably going to be up. So no doubt about it. Okay, another thing that's happening on September the 1st, which is still part of the star party, is the zodiacal lights that's happening on September the 1st. But this happens early in the morning. So of course, we're sorry we're going to be up, and there's no chance, there'll be a greater chance of seeing it. So again, it's going to be just as bright as the Milky Way. It's going to be a pyramid. I do have a picture right there. So it's kind of like a pyramid here, as you can see here, and then it follows the path of the sun, that point there. And I'll just draw it out for you, the path of the sun. So, okay, now the twilight, basically the dark skies, we're getting to August right now. So I had a look in August the 27th, close to the star party, so around after 9 p.m. So when it starts dark for us for astronomical darkness, okay. Again, August, this represents, the black represents the absolute darkness for it. And then the gray area represents the different twilights that happen. So now the solar activities, I did have a look at this. I was quite impressed with it. Last month, nearly doubled. You can see here, we're blowing the bell curve. The red curve represents the predicted values of it. But as you can see here, we have the actual values or the predicted values of 106 and the monthly value of the actual observed value of 196. So again, we're going to have a greater chance of seeing some auroras. Now for the weather, it's only for a few days here, but you can see here, and it looks again promising when I last checked, especially for the Perseid meteor shower here and for members tonight. It looks like it's going to be a clear sky for us. So that's it. That's what I have for what's up for August 2024. Thank you. You want to call the next one?
Thank you very much, Brian. We'll just get it up.
Yeah.
If I'd like to welcome Florent Thibault for what's new, modeling black holes merging.
Okay, is it working? Higher? Like this? Hello? This?
Yeah.
Okay. Okay, it's good. Hi, so hi everyone. Thank you for having me here. So I'm an undergraduate student at Concordia University in Montreal in physics, and I'm doing a summer research project this summer at the University of Manitoba with Dr. Stanley Woods and Sophie Arp. And our project is on modeling black hole mergers from supermassive stars. So a little bit about myself, real quick. So I have a twin. She looks more like my big sister than like me. I also love nature, kayaking, canoeing. And if you see me biking around town, you can say hi. That's me in Winnipeg. And really quickly to know what you know about the subject, if you could fill a poll on your phone or computer, you can go on this website and enter the code. Yeah, so I just want to get an idea of what's the level of background knowledge. Okay, okay. Okay, so thank God people know what a black hole is because it's a bit complicated to explain, but I can explain it a little bit. Okay, so thank you everyone. So let's start with gravitational wave, just to be sure we're on all the same page. A gravitational wave is just a wave like electromagnetism, but you can't see it with your eyes. You need special instruments, and it propagates gravitational field energy. And it was suggested by Einstein, and it's been used as a prediction of general relativity. So we can think of them as ripples in space-time. You can see this little animation. And so the different instruments we have to observe them, the first one is a LIGO, which detected the first gravitational wave in 2015, and LISA, which will be launched in 2035. So here we have a bit how LIGO works and the path that LISA will take. And the University of Manitoba is a member of both of those collaborations. Another instrument people use is the pulsar timing array. And those ones can detect more in the range of more low frequency gravitational waves. So Nanograv is one of the organizations that uses them. And so before we get the data from them, it's often useful to simulate those gravitational waves with simulations, coding, and stuff like that, so we can compare them with future observations. So this is why this summer project was born. And so here we can see the different ranges that each instrument can detect. Partial timing array is more in the nanohertz. LISA and LIGO have different ranges of peak detection too. So a black hole, I'm sure you all know, it's an astronomical object with a lot of gravity, so strong that light can't escape it. It can be described simply by its mass and spin, but today we'll focus on its mass. So the different ranges of mass, we have stellar black holes with mass under 100 solar masses. We have intermediate mass black holes with mass between 100 and 10 to the 5 solar masses. And we have supermassive black holes with mass over 10 to the 5 solar masses. And the redshift is something we use instead of saying 100 million years ago, you say redshift. So it's a measure of how old the universe was when the signal was emitted. So the more we go back in time, the bigger the redshift Z is. So today it's Z equals 0, and at the Big Bang it was infinite. And a binary is just a pair of something, but today we're going to talk about binary black holes. So two black holes that orbit around one another. So here are various gravitational waves that were detected. You have different black holes orbiting around one another, and they each have different masses, different parameters, and they will make different gravitational waves with different frequencies. So here it is what it will look like. So you can see different masses give different frequencies. It looks different, but it's all very fast. So that's the gravitational wave emission part. So classically, how those gravitational waves come into play is in the formation channel of supermassive black holes. So in the more recent years, so at low redshift, you could have two galaxies merging. So that means their central black hole would also merge together, and they would go through several physical processes to become closer to one another and merge. It will go through dynamical frictions that are scattering, and finally gravitational wave emission at the very end. So holodeck is a simulation built by Nanograv. So the guys, like said, use the pulsar timing arrays to detect gravitational waves. And in the in binary black holes, they can simulate this classical formation channel for supermassive black holes. So they can simulate the merger of black holes in different galaxies. And this simulation is very complex. It's based on another simulation called Illustris. Illustris is like a simulation of like a universe with a distribution of mass, the velocity of that mass, the stars, the dark matter, blah, blah, blah. It's very complex. So they basically take Illustris, and they take the binary black holes that are in Illustris and then evolution them. So when someone uses holodeck, they don't input what binaries there are. They just click play and here you go, the binaries, evolution. So this is the classical formation channel, but we're not sure if it's a true formation channel. So that's why we want to explore other formation pathways in case the classical one isn't the right one. So the azotic formation channel, it begins with a POP3 star, population 3 stars. Those are the first generations of star. They are very metal poor, which means they are mainly composed of hydrogen and helium. So for the formation channel, we start with supermassive POP3 stars. And since they're so massive, they can directly collapse into intermediate mass black holes. And with that formation channels, those two black holes can be in the same region. Unlike in the classical formation channel, they were in different galaxies. So much earlier in the age of the universe, those two can form binaries. And once they merge, they can form supermassive black holes. So when you want to simulate the merging from binary to supermassive black holes, you want to have 4 parameters. You want to have the initial mass of each black hole, the initial redshift, the time at which the merger began in the age of the universe, the initial separation between each black hole. So A2 is the biggest distance between the 2 black holes, so you just take half of that. And the initial eccentricity of the binary. So the eccentricity is just the shape of the orbit of the 2 black holes. So how we worked on holodeck, we changed it so that the user could give the program what we wanted the binaries to be. So we gave it a range of mass between 10 to the 4 and 10 to the 6 solar masses, beginning redshift between 6 and 15, a beginning separation between the 2 black holes between 0.1 and 0.2 parsecs, and an initial eccentricity of anything between 0 and 1. So all those ranges were chosen based on literature, but we'll continue to work on finding more accurate ranges in the future. So what we did this summer was only focus on the gravitational wave emission part and not all the other astronomical processes, which will be added later. So if you didn't know, a parsec is just a measure of distance, like kilometer, just a little bit slightly bigger. So basically how the modified version of holodeck works, you input those 4 parameters into the program, you click run, and it will output the final version of those parameters. So final mass, final redshift, final everything, and the time each binary took to merge. So okay, this looks scary, but don't be scared. So we told the program to choose random parameters, random distributions of parameters within the range given. So it's like pretty random, right? And just if you know how to read those plots, if you want to know, the darkest spots is where there are more binaries, because that run had 1,000 binaries evolution. And then after the evolution, you can see that it's there's a change, so that's good. The Z is lower than the beginning one, since the evolution forward in time, so that's good. We don't have time travel yet. The separation between 2 black holes is very small now, because they converged together, they merged until they were at the same point in space. And the eccentricity is very small because gravitational wave makes the orbit more circular. So yeah, that's all I want you to see in this plot. It's complicated, I know, but don't worry. And the other thing, the program output is the merging time for each binary. So if you have 1,000 binaries, you can see how much merged before 7 gigayears, before 13 gigayears, 20, 30, 40, etc. And the important thing to know when you make predictions like that, it's whether the merging time is smaller than the current age of the universe. Because in astrophysics, we consider something observable if the merging time is less big than the current age of the universe. So in this run, you can see that most of the binaries merged before the age of the universe. So we would consider those gravitational waves as being observable. So it just means like it's going to happen soon enough that maybe humanity will still be alive to see it. And if we compare the results of merging time from the simulation to this formula that's in the literature from someone else, we have a relative error of 30%, which isn't too bad for like our first runs. So this formula, it looks complicated too, don't worry. Just know that in the literature, the merging time depends heavily on the separation between the two black holes, so A to the power of 4, and to the and it also depends on the inverse of the total mass of the two black holes. So with this simulation, we hope to explore this new formation channel, and we also determined that those gravitational waves produced from that new formation channel could probably be observable, but there's still a lot of work to be done. And for example, we need to include the other processes that the black holes use to merge together. And we need to determine if LISA will be able to detect that, because observable means it's going to happen soon enough, and detectable means that specific instrument can see it. So, and after LISA gets its data, hopefully we could compare those results with the simulation results of gravitational wave. So yeah, I would like to thank my formidable colleagues, family, and friends who have helped me get this far. And thank you for listening. Any question? Questions are welcome. Yes.
So you're talking about the population 3 stars become black holes, and this is formation channel here. And I wasn't sure if I understood. So with this, would it be 2 population 3 stars already in a binary and each would become black holes, or would they be separate objects that would then somehow interact and?
From what I understood, I think they don't necessarily need to be in binary already.
I guess it doesn't matter for the gravitation part.
Yeah, but with that formation channel, I understood that they could be in the same region of space when they are formed, contrary to the other one. But yeah, maybe Tyrone later. He works with me on that. He knows more about top 3 stars. But yeah, good question. Yeah. Did you have another question?
My second question, you said that gravitational waves makes orbits more circular.
Yeah, strange, isn't it?
Yeah, what is that? Have things that in an elliptical orbit, but then as they get closer and they start to gravitational waves, the orbit will change and circularize.
Yeah, so at the end of the gravitational wave emission part, before they merge, their orbit is more circular. Yeah. I don't understand it either, but yeah. Yeah. I haven't delved into that yet, but it's interesting, yeah. Yes.
So what was your major difference or finding between your traditional model and this model? What was the difference?
One of the main difference is the time at which the supermassive black hole is formed. With the new formation channel, you can have supermassive black holes at higher redshift. And while with the traditional formation channel, you expect them much later in time. So that's one of the things. I'm sure there are other things, but I can't think of them right now. Yeah. Yeah.
I've heard that one of the great questions in cosmology today is why there are so many supermassive black holes, how they had time to actually form
Yeah.
in the time period or lifespan of the universe today. Does your research help enlighten us as far as how that's happened?
Yes, so yes, a lot of people work on this formation channel to try to explain how we can see supermassive black holes so early in the universe. Yeah, exactly. Other questions? More questions are better.
Other questions? Again, thank you very much, Mark.
Thank you. Thank you.
Thank you. That's great. So I just want to say a big thank you to Flora because it's really, really nice when we're able to collaborate with the University of Manitoba, and in particular when undergraduates are able to come in and talk about some of the research they're working on and just share a different perspective on what's going on in our universe. So I really appreciate that. Appreciate the U of M and reaching out, and also to Judy Anderson. For a lot of these may not recognize, but Judy puts in a lot of time working to get enough speakers for us to come out and talk about different topics. So not to, she hates the spotlight putting on her, but it is a huge, huge job and a lot of work. And I just want to say thank you again tonight to Judy for the amount of work that she puts into making sure we have a lot of really stellar lineup for the evening's presentations. Thank you, Judy. So we're going to take a short break for those of you online. We'll come back at 8:30 in about 15 minutes and welcome our guest speaker. So we'll take a short break, 15 minutes, and back at 8:30. Thank you. We're gonna get started here in just a moment. If you'll take your seats, please.
We're just sharing it right now. I like to turn the room lights down. I just don't want people to be falling.
Yeah.
Yeah. Wait, so I don't like the live. I don't like the live.
We're gonna start. And again, welcome to those of our who are joining us online. And just like to introduce our guest speaker tonight. Dr. Tyrone Woods is an assistant professor of physics and astronomy at the University of Manitoba. He studies the physics of some of the most energetic events and objects in the universe by combining theoretical models with observations across the electromagnetic spectrum. He is science co-lead for the Castor mission, a proposed flagship Canadian space telescope. Before returning to Canada, he completed his PhD at the Max Planck Institute for Astrophysics in Munich, Germany, and held research fellowships in Australia and the UK. Please welcome Dr. Tyrone Woods.
How's that? Can everybody hear me okay? Perfect. Try to stay a little bit back, keep the feedback at bay. Okay, so I'm going to talk a little bit about a very big project that's happening right across the country. But first, I wanted to mention a little something local that we've had going on at UM that I think is going to be near and dear to a lot of folks in the audience. Let me see if I can advance it. I'll probably have to click. There we go. Okay, so we are actually carrying out some upgrades at the Glenlee right now. Actually, there's going to be big work happening just on the 15th. We're going to wait a little bit after everybody's out there for the Perseids. The Ewan's campus telescope, the ECO, that's on the pier out there, the newer telescope that we've had, is going to be moved back temporarily to the campus rooftop over at University College Lecture Building. So that we can make room for the time being for a brand new CDK 350 with a new hatch dome that's going to be remote operable. In principle, to start, this is going to be just remote operable from UM campus, but we're hoping to make this something that people in the RASC may be able to use down the line as well. So if you really want to do some observing, but it's -40 out there, This will be an option down the line, so watch this space. Might be a good idea even to have somebody from the Glenlee upgrade team come maybe give a what's new talk as soon as this is sort of ready for first light. Okay, so on to the main event. Scaling up to sort of national, in fact, international projects. I want to talk about the #1 priority in space astronomy in Canada today. And I can say this confidently because I know that this is roughly the team of universities we're talking about that is involved, spanning the entire country. This is all of the members of the Association of Canadian Universities for Research in Astronomy, or ACURA. Basically, right across the country, we work together and we do this. It's a really great thing. Whatever field of endeavor you're working in, I highly recommend you talk to other professions in your field and recommend you do this. We do a decadal planning exercise. Every 10 years, we get together and we say, where do we want Canadian astronomy to be going? What do we want to prioritize in terms of funding? What do we want to do? What's the next big thing? And our #1 priority is to build Canada's first flagship space telescope, Canada's answer to the Hubble. This is something that we've actually been working on for getting towards about 15 years now. This was actually first discussed in the previous decadal planning exercise from 2010 to 2020. But it is now Canada's top priority in space for the next decade. This is the same document that has recommended things like Canada getting involved in the Square Kilometre Array, the big international radio array that's coming together, and getting involved in things like TMT as well. Why do we want to build a space telescope? Why do we want to get to space? Why is it so important that Canada have its own flagship space telescope? Well, I'm going to answer all of that, but I want to start just to make sure everybody really understands why, by taking it all the way back and say, why do we want to do space? Why do we want to do astronomy from space at all? It's very expensive. Well, there's two main reasons. If we can go to space, why would you want to do it? Well, it has to do with what we can see and how well we can see it. Simple as that. Let's start with what we can see. What we think of as light, of course, is just really a narrow range of wavelengths that you know, just from red to violet, you know, 300-400 nanometers tops. Little slice of the total electromagnetic spectrum, stretching all the way from the radio up to gamma rays, up to very, very high energies. Most of that light, though, the reason, by the way, that our eyes are so adapted to this narrow range is because our atmosphere is relatively transparent in this narrow range of wavelengths, this narrow range of colors. But there's so much going on in the universe at very, very low energies in the radio and at very, very high energies. The Earth, of course, is pretty transparent to radio waves, and that's why they're so great for communication, but you kind of need to have giant eyes for the optics to work out to see in the radio. So that's why we end up with this narrow range in what we call the optical. The atmosphere, quite mercifully, by the way, blocks most of this out. You know, even just dipping into the UV a little bit, the little bit of UV transparency in the sky, quite bad for our skin, of course, and it gets really, really bad as you go to higher and higher energies. But as I said, there's so much going on. This is our nearest big galactic neighbor, M31 Andromeda. And you can see it in the visible in the middle, and you can see all of the, you know, sort of standard stellar population that you would expect, but you can go to the infrared and you can see the dust, you can go to the radio and you can see the gas that will form stars. You can go to the ultraviolet and see the most massive stars and all of the, you know, accreting highly energetic objects, exploding supernovae, black holes accreting gas. You can go to the X-rays and particularly see some of those most energetic, these compact binaries, where black holes, neutron stars are accreting matter, white dwarfs are accreting matter and burning it on their surface. Very, very exciting things. Key things that we need to follow up in order to understand and answer basic questions about how stars form and evolve, how they make all of the elements that are necessary for life, how they shape their environment around them and lead to the next generation of stars. Basic scientific questions. We need not just this little narrow band of the optical, but the full electromagnetic spectrum. So that's one reason. Another reason that we go to space is because, as you probably noticed the last time you flew, the air can be quite turbulent. And this is very bad, as I'm sure many of you have noticed if you've gone out observing. You see this characteristic twinkling in the stars, of course. The atmosphere, random motions in the air produce distortions. And this is very, very annoying if you're trying to do precision measurements. It really puts a fundamental limit on the resolution of any kind of image you can make from the ground. You can beat around it a little bit with things like adaptive optics, but we won't get into that now. And really, it can only get you so far. To show you an example, here's Subaru. This is a cutting-edge telescope trying to image a galaxy. Here shown on the left, top left is the image, and then sort of a cutout below. We show what the zoom in is on the left. This is a cutting-edge telescope on Mauna Kea, best sites to observe on the surface of the Earth. And it's an 8-meter telescope. It's huge. Hubble is a space telescope. It's smaller, but it doesn't have to look through the atmosphere. It's only about a 2.4-meter telescope, but it doesn't have to fight its way through Earth's atmosphere. And so you can see the extraordinary difference in the resolution that you can get between left and right. If we translate into what does this mean for the science? Okay, it makes a prettier image, but why is it worth the billions of dollars that Hubble cost? Well, I like to liken it to, as a more down-to-earth example, if you're trying to understand, say, traffic in a city, right? You're trying to understand, okay, where are the points where traffic is building up? How do I help people get through the city faster? On the left, all we've got is how long, one data point for the whole galaxy effectively. It just looks like a smear. The traffic analogy would be all we know is the average time people spend in traffic. Can't do a lot of civic planning with that. Versus on the right, we've got an extraordinary detail. We can zoom in, and we can see, oh, this is where the stars are forming, or by analogy, oh, this is the not so well designed intersection, right? This is the kind of thing that we can do precision astronomy, precision science, when we have high resolution images from space. So, as I alluded to there, really the workhorse, the revolutionary instrument we've had for 34 years now is the Hubble Space Telescope. And it's been, of course, doing an absolutely amazing job. It's done astounding things over the years. I could give a whole summary talk. I could give a whole course just summarizing all of the amazing things that Hubble has done. Following Schumacher-Levy 9, tearing into Jupiter, to revealing the accelerating expansion of the universe from supernova observations. I think the most amazing, the boldest experiment that Hubble ever did was the Hubble Deep Field, though, when we decided, let's just take this patch of sky that looks basically empty and let's just stare until we can see all of the extraordinary faint things that are there. And we see this seemingly empty patch of sky is actually just teeming with galaxies, distant galaxies, but they're there. But Hubble's getting over. Earlier this year, we found out that Hubble is down to 2 gyroscopes from an original 6. That's bad. Hubble needs at least 1 working gyroscope, plus its other instruments now, instruments that would have, like its magnetometer, that would have otherwise been doing other science, now sort of dragooned into helping it point, and then it's increasingly limited in terms of what it can do in tracking and pointing as it gets older and older. It's getting on now. Space is not a particularly friendly environment for operating in. It's a 34-year-old telescope now. We need to talk about a replacement for Hubble. We can probably last, for a little while, probably till the end of the decade. But we need something else. And in many ways, there are a lot of other telescopes that are coming that are going to replace Hubble. What was once one telescope's job for the next generation is going to be many others. Some of them we've already launched, of course. Most famously, the JWST. And of course, the JWST has been doing extraordinary things here. I'm sure you've seen all of the breakthrough first images before, extraordinary images of the Carina Nebulae, the formation of stars, stellar nursery, to the death of stars as the planetary nebula, to Stephan's quintet, showing this collision of stars, one of which has a accreting supermassive black hole at its heart, to its own JWST's own deep field image, which was able to do, in hours, what took an enormous amount of accumulated integration time for Hubble. But JWST can't do everything that Hubble can do. Particularly, it's limited to, it goes much further into the infrared than Hubble ever could, but it stops short at about sort of yellow-green in the optical. Doesn't go any further than that, whereas Hubble was an infrared, optical, and UV machine. So what else is happening? Well, the European Space Agency recently launched Euclid. This is another project which Canada is involved in, actually, through a very interesting partnership process that would be the great subject of another talk. I should mention that Canada played an integral role in building the JWST. We do a terrible job of telling people about these things. Does anybody know what Canada contributed to the JWST? You don't get Scott, I know you don't. You know the answer. So Canada actually contributed 2 things. We contributed the fine guidance sensor. The reason that JWST can produce such extraordinarily well-calibrated pointed images, the reason that we can take such incredibly carefully precise images is because Canada built a fine guidance sensor so that JWST could point. And then the other thing that sort of partnered with this contribution is the near infrared imager and slitless spectrograph, or NIRISS. This is basically, it's a really cool thing. Basically, it allows us to take spectra of low resolution spectra of lots and lots and lots of objects in the night sky, and also take very, very good spectra of things like planetary atmospheres in transmission. So when you hear about, oh, there's evidence that there may be life on a dwarf planet around a distant star, if it's using JWST spectra, it's probably using a Canadian instrument to do that. That's something that we built, and we should talk about it more. So Euclid is another infrared instrument that the European Space Agency recently launched, which is going to be doing also, as I said, infrared observations. Its goal is to chase down, basically trying to understand how the expansion of the universe really works. We know that there's this thing that I alluded to, the acceleration of the accelerating expansion of the universe. It's being driven by something called dark energy, but we don't know what this dark energy is. And so Euclid is going to be looking at, by several different means, trying to understand how the universe's expansion has changed over billions of years of cosmic history. And to do that, it's going to be looking in the infrared, but over a much wider field of view than JWST can. It can't go as deep into the night sky as JWST, and given the same amount of integration time, but it can look over a much larger field of view. So it can build the kind of sample size we need to do, the statistical studies we need in order to sort of dig into this dark energy problem. And it's going to do a lot of other science along the way. NASA is actually developing its own answer to the Euclid telescope, the Roman Space Telescope, which has a bit of an interesting history on its own. Some of the hardware may be hand-me-down from other more national defense uses. But, well, that's worth a talk on its own as well. The Roman telescope, by the way, named for Nancy Grace Roman, really one of the chief architects of the Hubble Space Telescope, honoring her legacy as really a pioneer of space astronomy at NASA. So Roman is going to be, again, an infrared telescope looking at a wide field of view. It's going to have slightly different priorities than what Euclid has been trying to do. Euclid, it's a dedicated, we are going after dark energy. Anything else that you can, any other science that you can do with our data, cool, but we're mainly just trying to understand dark energy. Roman, you're actually going to be able to do what are called guest observing proposals. So basically scientists from around the world are going to be able to pitch for, I want to try to find exoplanets floating between the stars, or I want to try to understand star formation in distant galaxies, various other, sort of a more multi-purpose kind of science instrument. But you'll notice, amidst all of that, a recurring pattern. All of these telescopes are built up to one side of the electromagnetic spectrum. They're all focused on the infrared. Oops. How did that happen? Well, part of the reasoning here is really that many of these missions ended up taking a lot longer than they were supposed to take to get built, as happens. And so it was kind of taken for granted. Well, Hubble will be there to cover the ultraviolet. But as the years went by and as Hubble has continued to degrade, we're in a serious problem in astronomy. We're facing a serious problem in astronomy. This whole side, as you move much, much further out, okay, there are X-ray telescopes, there are gamma ray telescopes, but the UV and the blue optical, we don't really have a good answer post-Hubble. And more so, as we move towards more and more of these wide field astronomy instruments, we don't really have something that can do that in the UV. But there's so much going on in the UV. And so that's, we needed to understand, things, critical questions like, why do massive stars explode? How do massive stars form? How do black holes get so big? How do some of them become supermassive black holes? As we heard about earlier. I talked about understanding dark energy. Well, we also need the UV to constrain and understand dark energy and dark matter and answer big questions about what the fate of the universe is. I mentioned trying to understand the atmospheres of planets around distant stars. One of the things we found out from the JWST's pioneering observations is that infrared spectra of these exoplanet atmospheres is good, but it's really, really hard to tell apart certain spectral signatures, like the signature of a water in the atmosphere of a distant planet, from other contributions, say, reflection from the star, from the star's atmosphere, from the star's light coming through. We really, really need the UV in order to be able to tell these apart and to actually say, yep, that's a planet that could potentially be bearing life. So we need a new telescope that can answer these critical questions for the post-Hubble era. And so that's what Canada's proposing. Here, I'm just going to show sort of a really quick, I like to call this the baseball card stats for what we're talking about when we're talking about the Cosmological Advanced Survey Telescope for Optical and UV Research, which is really a mouthful. So we just call it CASTOR because it's French for beaver, it's our national symbol, and because, of course, it's quite a famous star in the sky. So we're talking about a relatively wide field instrument. Quarter of a square degree. It's about the size of the full moon. That's the area on sky it can look at all at once. It's going to be able to it's going to have roughly Hubble-like resolution, 0.15 arc seconds. It's going to have simultaneous observations for photometry. So seeing a large image in one color at a time, but it's going to be able to see 3 colors at a time, roughly speaking, UV, U, and G band. And it's going to be able to reach a limiting magnitude of 27 in 600 seconds, a small fraction of its expected orbit. Now, if you don't have a good intuition of what AB 27 is, think of the faintest star you can see with your naked eye. Now think of something 250 million times fainter. That's about what we're talking about in a 600-second exposure. It's going to have an ultra-high precision photometer. So this is something that's going to be able to tell apart as you watch the light from a star vary over time. It's going to be able to see variations on the order of 10 parts per million. That's going to be able to allow it to hunt for Earth-like worlds. It's going to have a couple of different spectroscopic modes. It's going to have something called GRISM spectroscopy, which essentially, short version, you're sending the light through a grating and a prism so that you're getting a low resolution spectrum of basically everything in the field of view. They'll all be overlapping. You need to use very complicated software in order to pick these things apart, but it's an enormous amount of information that you get all at once. It's also going to have an independent parallel instrument that's called the UV multi-object spectrograph, or MOSS. It's going to be powered by a digital micromirror device. This is the same type of little array of teeny tiny mirrors like you have in a projector. They make them, Texas Instruments makes them. It's probably what's in that projector right now, certainly in movie screen projectors. And it's going to be, essentially the idea is I have all of these teeny tiny little mirrors, so I can send some light this way, some light that way, and take the spectra of, in principle, hundreds of objects. We're planning for a minimum 5-year mission. So the idea is we would be aiming for launch in about 2030, 2031, minimum 5-year lifetime is what we've planned for, but realistically, given the technology that's going to be going into it, that most of which has been battle tested in other Canadian efforts, which I'll talk about in a minute, we're expecting it should be able to last 10, 15 years. I said launch 2029, I should say 2030. So just to give a bit of a more context about what this means in terms of getting a much larger field of view in the UV. So this is again our friend Andromeda. On the left, I have all of these little red squares. These are different pointings from a Hubble Treasury program meant to map a third of Andromeda in high resolution and extraordinary detail to a great depth. And this has been, an incredibly useful resource for astronomers who want to understand how stellar populations look as in different parts of a galaxy, how some stars produce cataclysmic events and others don't, how galaxies live and evolve over time. This is sort of our main benchmark because, you know, it's hard to, you can't get out of our Milky Way and look down on it, right? Not anytime soon. So M31 provides an amazing sort of comparison example of what a nearby big galaxy looks like. On the right, Castor will be able to provide the same depth and the same roughly resolution in 6 pointings. And in a small fraction of the time it took for Hubble to do what it had to, it just did to map just a third of Andromeda. So an extraordinary advance, orders of magnitude advance in the efficiency with which astronomy could do surveys. We could loop over Andromeda again and again and again and find all kinds of strange and exotic transients, things that flash in the night. Here's another way of illustrating how Castor is going to be really a new benchmark, a new landmark, the next generation in terms of resolution. So we have had some wide field UV astronomy before. In particular, NASA's GALAX mission was a famous example. But we never had that combined with high resolution. So this is a field of view, and you've got to believe me, these are galaxies, I promise, on the left, as observed by GALAX about 10 years ago now. On the right, a simulation of the same field of view as Castor will be able to see it. I know which one I would want as a wallpaper. And that's just in one color, of course. We'll get 3 colors simultaneously. Okay. I'm sure I meant to do that. So here's another example of this time, let's look at a globular cluster as imaged by Castor, as imaged by another telescope, UVEX. But the key thing I want to emphasize here, UVEX isn't a previously existing UV space telescope. UV is a planned space telescope. UVEX is a planned UV space telescope being developed by NASA, which is basically the next best thing, the only thing that's going to be out there if Castor doesn't get built. It's planned for sort of the end of the decade. Really, when it comes to doing high resolution wide field astronomy in space, in the UV, Castor, Canada's flagship space telescope, is going to be the only game in town. There are various other missions that have been proposed, all planning to be launched sort of by the end of the decade, maybe a year or two into the 2030s. Ultrasat, StarX, UVEX, all of them are going for very, very, very wide field, very, very low resolution. Sort of mostly because it's quite a bit cheaper, and also because the idea is, well, if we have to compromise, let's aim for at least finding things that other telescopes can follow up on. And there's some reliance here on the idea that Canada is going to lead, of course, a flagship high-resolution mission. So how do you build a flagship space telescope? How does Canada build a Hubble itself? Well, you've got to get a lot of people involved. So as I said, basically every university in the country, every university engaged in astronomy research anyway, is actively involved in one way or another in trying to get Castor built and planning out what those first 5 years are going to look like, what are the trade-offs in the design, how are we actually going to get this thing built. We have government partners, of course. So the National Research Council of Canada has really sort of been incubating this idea over the last 15 years. The Canadian Space Agency, of course, has been providing a lot of support. And sort of there's a lot of interesting nuances in how different government agencies contribute to, oh, this is this part, this is this part's responsibility, but this is this part's responsibility. But that's not an interesting talk. We've also got dedicated international partners. So actually just this past year, at the beginning of the year, the UK Space Agency signed a bilateral agreement with Canada. We want Castor, we want to get on board. So they're committed to supporting us in our continued development of the Castor mission. They're ready to build Castor. And so they're going to be providing, well, actually it's a UK company, Teledyne, who's going to be, Teledyne E2V, who's going to be providing the state-of-the-art detectors that Castor is going to be using. CNS 303s now. And these are going to be sent to JPL, who's been another long-time partner, who have a you might say sort of a secret sauce, a special delta doping coating they're going to provide to the detectors to make sure we have the most sensitive UV detectors ever. The National Research Council of Canada, along with France and the University of Colorado Boulder, has also recently started a new collaboration. They're now committed. They're helping to build that digital micrometer device, UV MOS, the tiny array of tiny little mirrors that I was talking about before. And there are a number of other partners that are hoping to get on board, Spain, Korea. Happy to talk about those soon. But we also have, as I said, maybe didn't mention yet, some key industrial partners. Castor is going to mean jobs right across the country. So our prime contractor, the people who are sort of overseeing the overall design from the industrial side, the engineering side, that's Honeywell Aerospace. They have labs all over Ontario. The people who are going to be working on a lot of the electronics and the interior optical design, that's ABB, with offices all over Quebec. The actual satellite bus, the spacecraft, if you will, that's going to be hosting, that's going to be the telescope is going to live in, that is going to be built by Magellan Aerospace. Does anyone know where Canada's Magellan Aerospace Lab is? Right by the airport. That's right. And if you ever get an opportunity to visit, I promise, it's really, really outstanding. This is actually, it's way bigger even than it looks here. This is just a sort of a very carefully chosen angle that doesn't include some things that they don't want on camera. But the Advanced Satellite Integration Facility is just an amazing place that we have right here. We've done amazing things in Winnipeg. It's not one of these things that we haven't really talked about. Has anybody heard of RASC? Yeah, so the RASC constellation, again, this is why I believe that we can feel so confident that Castor is going to probably be able to live a lot longer than 5 years, because we know that the satellite bus, that chassis, that framework that it's going to live in is battle tested. Magellan built the satellite buses for the RASC constellation. They're working on lots of projects all the time. Folks who've been in the museum will know that they built the Black Brant rockets that have been successfully doing suborbital flights for years. We used to launch from Churchill, actually. Recently, they're working on Red Wing, which is a government satellite that will be doing important things in space. But yeah, it's just an amazing place, and also an amazing place for students and postdocs to work as well. I'm visiting with Paul Harrison, lead engineer there, and Michelle Cow, one of my students. And yes, I did have to have a hairnet for my mustache because they were out of mustache nets, which is a thing. So while we're working on the engineering, we're also working on the science definition. You're going to build a big mission like this, you need to know basically from day one, day zero, what this telescope is going to be doing. It's pretty tightly scheduled the first 5 years. And so to make sure that we're getting the most science return that we can from all of this, we had 8 teams, each with a Canadian lead, but we also have international partners, as I mentioned, folks who've been working with us along the way. On basically anything you can think of in astronomy, everything from trying to understand dark energy, as I said, to trying to understand the evolution of supermassive black holes and cosmic time, to trying to find strange and exotic supernovae, and understand why some of them produce such unusual abundances of elements, to trying to find evidence of habitable worlds and map the outer solar system. All of these things, we've had teams working across the country, carefully planning out what those first 5 years are going to look like and how we're going to accomplish all of these goals. Any one of these things, by the way, in principle, if we could come up with answers for these questions, these are, not going to jinx it, these are Nobel Prize winning kind of questions here. One of my favorite things about the development of Castor over the phase 0, as we call it, sort of this planning phase that we've just completed, is that we get to have so many students involved, the next generation involved in planning what this great telescope Canada is working on is actually going to be able to accomplish. Doing things like, exposure time calculators, deep field simulations, modeling this spectroscopy. It's incredibly exciting work, and it's so great to see so many people doing just world-leading research right here in Canada. All right, how am I doing on time? Good. Oh. So for the second part of the talk here, let's talk a little bit about some of the secrets that we think Castor is going to be able to unlock about the universe, at least in that first 5 years of its mission. So there's 16 proposed legacy surveys. These are the big treasuries of data that we're hoping to leave, not just for the next generation, but for generations afterwards. And they have big ostentatious names like the Legacy Survey for Astrophysics and Cosmology, and rapidly responding to the dynamic universe. So what do these things mean, right? What are we talking about? Well, one of the things that I'm really excited about, Castor is going to hunt down the origin of all the gold. What do I mean by that? Well, so we know these things called, who's heard of a kilonova? I should have, like Florent had, I should have one of those fancy widgets where everybody can put it on their phone. But, so a kilonova, we now know, it's not as big an explosion as a supernova generally, or it was thought to be, but it's much, much bigger than classical recurrent nova. We now know that these are actually the mergers of neutron stars, a binary pair of neutron stars, two neutron stars in the same solar system, losing energy and angular momentum as they shake space-time itself, and that draws them into a closer orbit until they finally merge and produce an extraordinary explosion, which produces a lot of light. And it produces a huge booming gravitational wave signal, that shake in space-time itself, which we've actually been able to detect on Earth. And for a very, very famous event in 2017, we were able to detect a gravitational wave event at LIGO, and we were able to correlate that with a whole bunch of optical and UV and other observations and say, look, this is a kilonova. And we were able to take the spectra of this object and realize that it was producing an extraordinary number of heavy elements, extraordinary abundance of heavy elements, in particular, an extraordinary amount of things like gold. And if you add up all of the rate of these kilonova that we think that they're happening at, and you look at how much gold this one produced, it looks an awful lot like these kilonovae actually produced all of the gold in the universe. Okay, but how did they do that? Well, it turns out we don't really know. Because this kilonova didn't really look, this first one that we got all this data on, we'd seen them before, but getting all this data at once, getting gravitational waves and the light and electromagnetic observations at the same time, it didn't really look the way we thought it did. We thought it would, based on models. And there's a few different ideas as to why. And without going too far into the nitty-gritty, it turns out that the key thing that we need in order to disambiguate between these models and to understand what's going on as these two neutron stars merge, more gravitational wave observations, but also we need ultraviolet observations in the first few hours of the explosion. That is something that Castor is going to be able to deliver. And the reason is we'll be able to get, especially with things like advanced LIGO, a gravitational wave signal forewarning. Hey, wow, everybody, quick, look, there is a kilonova happening at roughly this spot in the sky. But roughly this spot is going to be a fairly large area, just because of basically the physics of the way light works. It's very good at finding these enormous distances, these shakes in space-time. It's not so great, mostly because of it's only oriented along sort of most of the LIGO sites are. It would be great if we had a LIGO Antarctica and a LIGO Arctic and things like that, so that we could figure out exactly where the gravitational wave signal is coming from, but we don't. And so our localization is not so great. We need something that can look deeply in the night sky over a fairly wide area and chase down, oh, that's the kilonova, and we need to be able to do it in a few hours. Castor is going to be able to do that. It's going to have the wide field of view, and it's going to have the ability to turn around on a dime effectively as soon as it gets the command to do so, to start hunting for these extraordinary events. Castor is also going to be able to reveal the detailed, high-resolution inner lives of about 1,000 of the nearest galaxies in the universe, big galaxies. So one of the legacy surveys that we're planning is basically a census of our local volume. So what's going on in all of these galaxies that we have the best chance of observing in high resolution, and really understanding what our neighborhood looks like, and understanding massive galaxies, understanding how stars form in different environments, understanding how sometimes star formation stops in some galaxies, but not in others. Why do some keep going? Understanding the dust reddening and things like that in these galaxies. This is something that we're going to be able to do in extraordinary detail with Castor. Also hunting for things, I think, one of the funnest things that I heard proposed was looking for, we have a big sample of galaxies in, sort of the local universe. Well, in our Milky Way, you don't get a supernova very often, but if you have 1,000 galaxies to look across, you're probably going to get a few supernovae over the next couple of years, right? And so trying to look for massive stars and build a catalog of massive stars before they've exploded, supernovae, so that we can then go back later and match, oh, that star is gone now. That must have been the one that exploded. So this is something that they've been able to do a little bit with Hubble, but Hubble has a tiny field of view relative to Castor. So this is something that's going to be really a powerful machine for. Castor is also going to be able to weigh. We picked about 1,000 supermassive black holes for a variety of different selection criteria, spread across 10 billion years of cosmic history. How do you weigh a black hole, a supermassive black hole, when it's incredibly, incredibly far away? Well, I didn't invent this. I just think it's really, really clever. It's this method called reverberation mapping. And so basically the idea is, all we're going to see, take this and send it out, megaparsecs and megaparsecs away. All we're going to see, even with Castor's great resolution, is a point of light. But Castor is extremely sensitive, and it's also going to be able to get spectroscopic data as well. So we can see this point of light varying over time, how much light we're getting at different wavelengths. In principle, some of this gas surrounding this black hole is ionized. That means the electrons are stripped off by high energy radiation from further in from the disk. The inner disk is very, very bright and very, very high energy photons coming out. Those strip electrons off, and then they recombine, and that produces emission lines. Light coming out at very specific frequencies associated with different atomic transitions. The gas is dense enough that those recombination times are actually very, very short. And so if the inner light source varies because the accretion time scale varies, then the different emission lines will also vary as the source of ionizing radiation goes up and down. Well, the handy thing here is we know the speed of light. And we know roughly where those different emission lines should be coming from. But more importantly, we know the time. We know the speed of light and we know the time. So what we can do is we can, by timing these variations, we can measure, oh, okay, so this emission line was coming from this far away from the black hole, and this emission line was coming from this far away from the black hole, and measure out the different, where all of the gas is relative to the black hole. But the gas is also moving in a disk. And that means it's going to have a Doppler broadening. Basically, the same way that as a car whips past you, you hear it get louder, you hear it fainter. Light, instead of doing that, it moves to the red. If it's moving away from you, it moves to the blue. If it's moving towards you in terms of the wavelengths that are being emitted at, you see a broadening in an emission line when gas is moving in a circle. How broad it is depends on the velocity of the gas. All of that is to say, from looking at how these emission lines vary, you can get how far away they are, and then you can get their velocities. You can solve for how massive the object is that they're moving around. And by doing that, you can weigh the black hole. Now, that's a pretty big mouthful. But the crux of all of that is that Castor is going to be able to carry out these precision measurements for, as I said, 1,000 black holes over 10 million years of cosmic history, tracing out how black holes grow over cosmic time, and some of them becoming supermassive black holes. Castor is also going to provide, this is another one of our legacy surveys, the definitive map in the UV of our own cosmic backyard, the Milky Way. For 1,000 square degrees, we're going to be mapping out in the UV, providing the foremost high-resolution UV map of the Milky Way, and answering key questions about how stars form in our own cosmic backyard, what the dust distribution is like, critical questions about how our own Milky Way is constituted. Castor is also going to be an incredibly powerful machine for mapping our outer solar system. I don't work in outer solar system science generally, so I was surprised by this, but it turns out that a critical diagnostic for understanding what these icy bodies in the outer solar system, like Kuiper belt, are made of, is by looking at sort of the slope of light. If you plot how much light is emitted as a function of wavelength, and you go further and further into the UV, the slope of how much light is coming out is a fundamental diagnostic of the composition of the surface of these icy bodies. And so you can actually figure out what these oldest building blocks of the solar system are made of just from looking at them in UV and blue light. It's astounding. And Castor is going to have the wide field of view necessary to map a large swath of the outer solar system. Finally, I alluded to this earlier. Something that Castor is really, critically going to provide in terms of missing ingredients in understanding of astronomy today is UV follow-up of suspected Earth-like planets. We really need the UV in order to be able to say, yes, for sure, this planet has water and nitrogen in its atmosphere and other things that we think, based on our one example, Earth, are absolutely essential for it to be habitable, maybe host life. And so Castor is going to be, I think, very, very busy following up on a lot of candidate habitable worlds in the 2030s. So all that is amazing. Where are we now? Well, right now, mostly, the science is all sorted. Phase 0 is done. That's sort of this planning phase that I was talking about. Now we're waiting for what's called phase 8. This is all project management jargon, but basically we're wanting to move from we're planning a mission to we're building a mission. It's a small step, but it's a big step. Beyond phase A, there's phase B. See, you don't get to actually launch the thing until phase E. It's it's another boring talk I could give, but the point is, we've actually put in a pre-budget submission to the Treasury Board now. We are awaiting a decision from the federal government. This is something that's going to provide jobs right across the country. That's going to provide, a iconic contribution to Canadian science. Probably, we have the Canadarm and the $5 bill now. I think Castor could be on the $10 bill, or 20, if people are still using cash. In terms of what is the actual financial ask that we need in order to get through the next year, it's actually pretty paltry. It's $14 million. I understand there's a lot of other budget constraints on right now, but all we need is $14 million to fulfill our commitment to the UK Space Agency, to JPL, to France, to our tentative partners in Spain and Korea, who are waiting for Canada to act to give us the green light to keep moving. Beyond that, if the extending grows, of course, $46 million extend to 3 years, total lifetime costs of about, can anybody guess what Castor is going to cost? It's only, to Canada, only $304 million. And our partners will contribute another $150 million or so. It's But compared to Hubble, which has a cost, if you're being generous, of $10 million. And that's not including many of the other contributions that have happened. Some of the other financial investments that had to be made over the years. As you may recall, Hubble needed a lot of servicing. So for a tiny fraction of what Hubble cost over the last 34 years, Castor is going to be able to revolutionize astronomy in this country and around the world. A legacy that will be carried forward for generations. And that is why it is our #1 priority for the next decade. And also, I guess just stop there. Thank you. Questions? Yes, Scott.
I got thoughts, but first answer would be cool.
Thanks.
Can you give us a sense of the size of the spacecraft, the size of the optics, what kind of rocket did we go on there? What, like, are we talking?
Yeah, so we're talking a 1 meter 1 meter diameter aperture. So it's smaller than Hubble, but it's got between the revolutionary detector technology that we've got there, it's cleverness with the optics. We can get down to the kind of sensitivities that Hubble was able to do in pretty good time. In terms of the housing all around it, I like to think of it. It's about a Toyota Tercel, so like a modest sized sedan. So it's something that you could launch in, say, a Falcon 9 or something like that. It doesn't need any of the big fancy stuff that people are talking about. Actually, the reason that Korea is interested in partnering with us is because they think it's a great candidate for their new space launch system. So watch this space. Yeah.
So I've got a question and comment. Maybe the comment first. I think Castor would be a great emblem for a $5 coin.
Yes, well, we'll get there.
But mentioned earlier that one of the things Castor could do was to inform us about why stars explode.
Yes.
How does UV do that?
So the stars that there's sort of, if you think about supernovae, so there's sort of two different types, broadly speaking. So there's type 1 supernovae that are very famous as standard candles. I won't get into all of that. Basically, they're always about the same luminosity intrinsically. So you can measure distances by just measuring the flux you're actually getting, right? And say, oh, okay, 1/r². Anyway, these probably come from exploding white dwarfs, low mass stars like what are some, most of which are happy to sit and cool for the next many billions of years, but about 1% of which explode for reasons we don't understand. We have a lot of ideas though. The other type of supernovae is a core collapse supernovae. These are when very massive stars reach the end of their lives. So we think, what keeps a star aloft? Well, first it's hydrogen burning. Hydrogen burns to helium, burns to carbon, to oxygen. It's a very massive star. It can keep burning on down until it burns to iron, which sucks in more energy than it releases when it burns. And so you get a collapse of the core until it basically, maybe the urge for neutrons not to be on top of each other can hold it aloft, in which case you get a neutron star. But if even that can't hold it up, it keeps collapsing into a black hole. The enormous energy release from that blows off the outer envelope and you get a type 2 supernova. In both of these cases, massive stars, their peak luminosity for these very massive stars is in the ultraviolet. If you want to understand populations of these objects, if you want to look for candidates long before they've exploded, you want to look in the ultraviolet. And for the low mass things, these type of supernovae, we think that many of them are probably coming from accretion onto white dwarfs. So it's another binary system. That's my bias, but a lot of the exciting things happening in stellar astrophysics are because of binaries. So you have solar system with two suns, matter is spilling over from one star onto the other, road, which is a critical pressure. So that again would produce a very UV luminous object. And beyond that, a lot of other transient phenomena that we're just learning about also happen in the ultraviolet. So again, you really need any kind of violent explosion, the kinds of things that tend to produce lots of heavy elements and things like that. You want observations in the UV both long before and also right before and also after, because there's just a lot going on. It's sort of where things are mostly radiating in these cases. Other questions? Oh, yeah, sure.
Does forecaster go into the infrared?
No, so you can only do so many things, especially on 300 million budget. So, Castor will basically look from about mid-green, really the middle of human vision, all the way out to about 150 nanometers. Yeah, so well into the UV, but about midway through human vision.
What kind of an orbit will be placed?
No, that's a great question. I totally skipped over that. I should have put in the slides. So it's going to be launched into a polar orbit, mostly for strategic reasons. We're a polar country and it's a lot easier to communicate with. So it's going to be in a polar sun synchronous orbit. So that's a specific kind of polar orbit where basically it's tracking the night-day perimeter, so that it can keep its solar panels pointed in the sun, but not be looking where the sun is. You want to minimize the stray light coming into the telescope. And it's going to be about in an 800-kilometer orbit. So that's the height above the surface. You want to go as high as you can, as your budget allows, because Earth glow and things like that contribute to background in the UV. We really want to beat that down.
Circular? It's a larger amount of Earth.
Oh no, it's nearly circular.
Just wondering if you can give us a little more information about the teledyne detector and like how that compares, for instance, with what's in Hubble. Like evidently the microelectronics has gotten much smaller.
Yes.
So, like for instance, megapixels, like how does it compare with other detectors out there?
Yeah, so we're talking about a I'm blanking on the number of meg. We're talking about a 960 megapixel camera. So yes, so it's going to be thereabouts. If you put that in. So it's going to be an enormously powerful high resolution camera, huge, absolutely. But a lot of the progress is also coming in things like this UV detector, this delta doping that I was talking about. This is that I quickly mentioned this secret sauce that JPL can provide. So basically, it's a CMOS detector that they're providing. So they're backlit for complicated condensed matter reasons that I can get into after the talk. So you see they're back illuminated, and then you have this delta dope coating, which improves the UV sensitivity further. So you're getting something that's orders of magnitude better. They were able to do 34 years ago. And then things like the readout electronics, which can be that world expert RASC really leads this. Also contribute to sort of this huge improvement over back in the day.
So given that it's going to be detecting or providing a much larger data set, perhaps improved image compared to what Hubble was doing, is there any issue with bandwidth?
Yes, there is. And that's a great question. And it's a very hopefully well-funded question. Essentially, Castor's data rate is expected to be right on the edge of what you can reasonably do with radio frequency communications. And so this has been leading some discussion of, do you scale back a little bit on the cadence of your observations, take a little bit less data? Or do you make that big investment in optical communications? So you can get very high bandwidth communications. This is sort of a state-of-the-art thing that's been incubated for a long time now. If you move from the radio to laser-based communication, and so radio frequencies, your receiver is a big radio dish. optical frequencies, or actually more likely it's going to be infrared, just into the infrared frequencies with lasers, your receiver is a telescope. And so between 40 centimeter to 1 meter telescopes would be receivers for these things. And so this is something that can get you into the many gigabits per second down. In theory, up to a terabit per second, but that's a little science fiction. That's way more than we need. So we need something on the order of a few to 10 gigabits per second if we don't want to have to scale back our data rate at all. And so that's well within, it's within the capabilities of the technology today, but it's not something that's been widely implemented today. So it's exactly the kind of thing that would be a cool thing to shoot for with just a little extra money on that 6 to 10 year time scale. Yeah, and I should also say that Canada has long been a world leader in radio frequency communications with space. We've got satellite stations across the country, even up in Nunavik. We've got ground fiber, so you get high speed to communications. It makes sense combining that heritage in communications and that heritage in astronomy that Canada should step into optical communications, but that's the proposal. Yeah, sure. I think Michelle.
Oh, I missed what's the aperture? What type of scope is it?
Oh, 1 meter. Yeah,
1 meter.
yeah.
Yeah, so where's all that data go?
Yes.
With square kilometer array, they've all been working on just the data side, storage and things like that.
Yeah, so in principle, so we're not in square kilometer array, petabytes per day. How do we do this kind of territory? We're talking about hundreds of gigs per day, so it's manageable. The main limit is like your path, unlike the square kilometer array, where a satellite that's passing over it, we need to get that down in minutes, right? Unless you have many sites, that's another option. Essentially, where that data is going to go, first to either our radio frequency or optical communications terminals, and then it's going to come almost certainly to the Canadian Astronomy Data Center, which, if you haven't heard of it, is an extraordinary resource that Canada has been funding for since the 80s, which is not a coincidence because that's about the time that Hubble's been around. Its original mandate was to be a satellite site for storing Hubble data for the Canadian astronomy community. And it's in Victoria, BC. It's associated with the National Research Council's Hertzberg Astronomy Research Center, which is really our national lab for astronomy. And did an enormous amount of work back 34 years ago in really laying the foundation for, things like the internet in Canada. So, there's enormous spin-offs that come from this. Yeah.
Is the spacecraft or the telescope components serviceable from space?
Yes. It won't be designed with serviceability in mind. In principle, one could. The key issue is that we don't have a vehicle right now that can, right? Like people talk about, oh, we should service the Hubble to save the Hubble. We lost the shuttle a long time ago. And it's not, it's possible that, a Falcon 9 could go up and from a capsule, you could work on something like this, but we don't have a very clear plan in place, is the honest truth, for how you would do things like that. So it could be service. It's certainly not JWST. It's not sitting out at L2, and it would be the biggest mission humanity's ever undertaken to go and service it and come back. The deepest in space we've ever been by far. We'll go to Mars before we send people to L2. You could in principle service Castor because it is going to be in an Earth orbit. It's only 800 kilometers up. In principle, if something went terribly wrong, something could be done. But I wouldn't say that we're planning for that.
Yeah, that just reminds me, what's the deorbit plan?
The deorbit, that is a fantastic question. Yes. So the deorbit plan is something that is still under study. That is something that would be funded by the phase A funding that we're talking about. But this is something that Canada is very, very concerned about. If you haven't been following the news on this, debris in low orbit is becoming a real problem. And we need to have a concerted plan for deorbiting anything put in orbit, because the more we put up there, the more dangerous it gets. And so we're working with folks like Aaron Woolley and UBC, who are experts in this. But we will have a concerted. Any other questions? Thank you very much.
So it's my pleasure to present you this little token of our.
Thank you very much.
In person, often our speakers are by Zoom and we have to mail them at ridiculous processes. But here's a little token, and I'm hoping that we might bail upon your kindness to come back and speak with us.
Absolutely.
Because I think it would be so exciting to hear updates all the time.
Absolutely.
Yeah, and especially on the short timeline. I might be alive by then.
Yes.
Thank you so much.
Thank you very much.
And just a couple of quick things before we close the meeting. There's still a few books left here up front if you're interested. And Florent or What's Up or What's New speaker would be interested in going out to Glen tomorrow night, and he lives in Saint Vital. So if there's anybody here who would be able to offer him a ride out and back, Florent's over here. So if you could connect with him, that would be wonderful. And if not, just let us know and we'll go from there. And again, thank you to our speakers tonight. And there's a meeting, get together over at Boston Pizza in Pembina. And I hope you all have a wonderful evening. And I look forward to seeing a lot of you out at Sprucewood Star Party and the long weekend of September. Have a good evening, everyone. Bye-bye.